This is problem number 8. There's a short answer to this problem, and there's a long answer. The short answer is r squared. Simply take r and square it. Now, mathematically, let's see what that means. So we'll take negative 0.869, and you have to square it. Hold on, I forgot. You're going to square it. Got to square the whole thing, so you have to square the negative sign. Correlation can be positive or negative, but the correlation coefficient r squared is always positive. When you square a negative number, you always get a positive number. Alright, we're going to square this. And so we get, let's call it 0.76. So r squared equals 0.76, or 76%. So what fraction of the variability in fuel economy is accounted for by the horsepower? And that would be 76%. And that squares with the definition of r squared, which has a number of definitions, beginning with the mathematical definition, which is simply the square of r, of the correlation between y and x. And r squared gives the fraction of the variability of y accounted for by the least square regression line on x. And that goes back to the question, what fraction of the variability in fuel economy is accounted for by the horsepower? So it's fuel economy versus horsepower. In other words, the more horsepower you have, you would expect fuel economy to go down. And then finally, the definition for r squared is an overall measure of how successful the regression is in linear relating y to x. So let's go back to here. So we have so let's get into sort of what does this really mean? Well, we have estimated fuel economy equals some starting point, some miles per gallon. Let's call it 10, which would be ridiculous. Let's say that's your fuel economy when your horsepower is 0. Or it's probably higher than this, probably much higher. Let's say it'd be like 100. Let's say you get 100 miles per gallon when you have 0 horsepower. You know, like obviously 0 horsepower is completely outside the domain. And then it would be minus some rate of change. I don't know, let's call it 1.2 horsepower. I don't know what the units for horsepower is. I looked them up a year ago or whatever. But anyway, it has some units. Maybe you know them. You scientists know them. So for every increase of 1 horsepower, the fuel economy goes down by 1.2 miles per gallon. And the fuel economy is measured in miles per gallon. The estimated. So this, I'm just making this up. This is made up. Okay, I'm just making up made up equation to illustrate. Now, what does this mean? Here we have a line of best fit. Here we have a model that attempts to explain fuel economy in terms of horsepower. So one variable is being explained in terms of the other. Okay, now how much of the change in fuel economy is explained by change in horsepower? R squared says that 76% of that change is explained by the change in horsepower. So 24% is explained by other variables as revealed in the residuals. And the residuals are E is a symbol for one residual equals Y minus the estimated Y. Okay, and it's this out of which R squared ultimately is calculated, or R and then R squared. So remember, the least squares regression line is the line that minimizes the residuals. But if you have a lot of residuals, then that least squares regression line is going to be affected by that. Anyway, so the short answer to 8, what fraction of the variability in fuel economy is accounted for by the horsepower? The answer is 76% of the variability in fuel economy is accounted for by the horsepower. So another way to, 76% of the change in estimated fuel economy is accounted for by the change in horsepower as shown in the model. 24% is explained by other variables as revealed in the residuals.